Sun. The Sun is the star at the center of the solar system. It is a nearly perfect ball of hot plasma that has been ignited by nuclear fusion reactions in its core. Light, ultraviolet, and infrared radiation make up the majority of the energy it emits. It is the most important source of energy for life on Earth. The Sun's radius is about 695,000 kilometers, or 109 times that of Earth. Its mass is about 330,000 times that of Earth, comprising about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen. The rest is mostly helium, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star. Consequently, it is referred to informally and inaccurately as a yellow dwarf. Its light is actually white. It was created around 4.6 billion years ago when a portion of a massive molecular cloud gravitationally collapsed. The majority of this material gravitated toward the center, while the remainder flattened into the solar system's orbiting disk. The central mass eventually started nuclear fusion in its core as a result of becoming so hot and dense. This process is thought to be the primary way that stars form. About 600 million tons of hydrogen are fused into helium in the Sun's core every second, creating 4 million tons of energy out of the process. The Sun's light and heat are produced by this energy, which can take anywhere between 10,000 and 170,000 years to escape the core. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times. The Sun was thought of by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of some solar calendars. The Gregorian calendar, which is the most widely used calendar today, is based on the common 16th century understanding that the Sun actually moves as observed. General characteristics. A G-type main sequence star, the Sun accounts for 99.86% of the solar system's mass. With an absolute magnitude of 4.83, the Sun is predicted to be brighter than 85% of the Milky Way stars, the majority of which are red dwarfs. Population 1, or a star rich in heavy elements, is what the Sun is. The shock waves from one or more neighboring supernovae may have served as the catalyst for the Sun's development. In contrast to the abundances of these elements in so-called population 2, heavy element-poor stars, the solar system has a large abundance of heavy elements like gold and uranium. The production of the heavy elements most likely occurred during endothermic nuclear processes during a supernova or through neutron absorption inside a huge second-generation star. With an apparent magnitude of 26.74, the Sun is by far the brightest object in the sky over the planet. The next brightest star, Sirius, is nearly 13 billion times fainter than this one, with an apparent magnitude of 1.46. The average distance between the Sun's and Earth's centers is 1 astronomical unit, or roughly 150 million kilometers, though the distance changes as Earth moves from perihelion in January to aphelion in July. The extreme values can range from 147,083,346 kilometers to 152,112,126 kilometers, while the distances can range from 147,098,074 kilometers perihelion to 152,097,701 kilometers. Light from the Sun's horizon to Earth's horizon travels at its average distance in roughly 8 minutes and 20 seconds, while light from the Sun and Earth's nearest points travels at its average distance in about 2 seconds slower. Through photosynthesis, this sunlight's energy sustains practically all life on Earth and regulates the planet's climate and weather. The density of the Sun falls exponentially with height above the photosphere, but it lacks distinct boundaries. The distance from the Sun's center to its photosphere, or apparent visible surface, is used to determine the radius of the Sun for measuring purposes. According to this standard, the Sun is a nearly perfect sphere with an oblateness of 9 millionths, meaning that the distance between its polar and equatorial diameters is only 10 kilometers. The Sun's shape is not considerably impacted by the planet's mild tidal influence. At its equator, the Sun rotates more quickly than at its poles. Convective motion resulting from heat transfer and the Coriolis force resulting from the Sun's rotation are both responsible for this differential rotation. The rotating period is roughly 25.6 days at the equator and 33.5 days at the poles in a celestial frame of reference. The apparent rotational period of the Sun near its equator, as seen from Earth as it revolves around the Sun, is roughly 28 days. The Sun turns counterclockwise around its axis of rotation when viewed from a location above its north pole. Sunlight and neutrinos. When observed from space or when the Sun is high in the sky, the color of the Sun, which emits light across the whole visible spectrum, is white, with a CIE color space index close to 0.3. When observed from space, the solar radiation at each wavelength peaks in the green region of the spectrum. Atmospheric dispersion causes the Sun to appear yellow, red, orange, or magenta when it is very low in the sky, and on rare occasions even green or blue. Although the Sun is often white, white sun rays, white ambient light, white illumination of the moon, etc., certain cultures perceive the Sun as yellow or even red. The precise causes of this are cultural and are up for debate. The Sun is a G2V star, meaning that it has a surface temperature of about 5,778 K and that it is a main sequence star like most other stars. The solar constant measures how much electricity the Sun puts per square meter of surface area that receives direct sunshine. One astronomical unit, EU, from the Sun places the solar constant at a value of approximately 1,368 watts per square meter, that is, on or near Earth. Because to attenuation caused by Earth's atmosphere, less energy, closer to 1,000 W/m2, travels to the surface during clear days when the Sun is near the zenith. At the top of the Earth's atmosphere, the Sun's energy is split roughly equally between infrared, visible, and ultraviolet rays, a total of about 50%, 40%, and 10%, respectively. Particularly in the lower wavelengths, the atmosphere blocks off about 70% of solar UV radiation. 98. The electrically conducting ionosphere is produced when solar UV radiation ionizes Earth's dayside upper atmosphere. Sunlight's ultraviolet rays have antibacterial qualities and can be utilized to disinfect water and tools. Additionally, it produces sunburn and has additional biological consequences including vitamin D synthesis and sun tanning. Additionally, it is the key factor in skin cancer. The amount of ultraviolet, UV, radiation varies significantly with latitude due to the Earth's ozone layer's substantial attenuation of UV rays, which has contributed to a number of biological adaptations, including differences in human skin tone around the globe. The solar plasma of the radiative zone almost instantly absorbs high-energy gamma-ray photons that were first generated by fusion processes in the core, usually after only traveling a few millimeters. Re-emission occurs at a generally lower energy and in an arbitrary direction. Radiation must travel through a series of emissions and absorptions before it can reach the Sun's surface. The photon travel period is predicted to take between 10,000 and 170,000 years. The neutrinos, which make up approximately 2% of the Sun's overall energy output, arrive at the surface in contrast in just 2.3 seconds. The timescale of energy transit in the Sun is longer, on the order of 30 million years, because it is a process that involves photons in thermodynamic equilibrium with matter. If the rate of energy generation in the Sun's core were to suddenly shift, it would take this long for the Sun to stabilize. The fusion processes in the core also produce neutrinos, but they seldom interact with matter, unlike photons, thus practically all of them are able to leave the Sun right away. For many years, observations of the amount of neutrinos generated by the Sun were 3 times lower than what theories anticipated. The effects of neutrino oscillation were found to account for this mismatch in 2001. The Sun produces the number of neutrinos anticipated by the theory, but 2/3 of them were missed by neutrino detectors because they had changed flavors by the time they were picked up. Solar System. 8 planets are known to be revolving around the Sun. Mercury, Venus, Earth, and Mars are among the 4 terrestrial planets, along with 2 gas giants, Jupiter and Saturn, and 2 ice giants, Uranus and Neptune. The solar system also contains 9 objects that are typically regarded as dwarf planets and a few more contenders, as well as an asteroid belt, several comets, and a significant number of frozen objects that are located beyond of Neptune's orbit. Numerous smaller things, including 6 of the planets, also have natural satellites of their own. An example, the satellite systems of Jupiter, Saturn, and Uranus resemble miniature replicas of the solar system in certain aspects. The gravitational force of the planets causes the Sun to move. The Sun's center is always 2.2 solar radii away from the barycenter. Jupiter, Saturn, Uranus, and Neptune are primarily to blame for the Sun's motion. The motion forms a trefoil pattern during some periods of several decades, but between these periods it appears more erratic. The pattern essentially repeats itself after 179 years, 9 times the synodic period of Jupiter and Saturn, but rotated by around 24 degrees. The same gravitational forces equally distort the orbits of the inner planets, including the Earth. As a result, the Sun's motion has minimal bearing on the relative positions of the Earth and the Sun or the solar irradiance on the Earth as a function of time. Solar space missions. The NASA Pioneers 6, 7, and 8 and 9 were the first satellites built for long-term observations of the Sun from interplanetary space, and they were launched between 1959 and 1968. These missions conducted the first in-depth analyses of the solar wind and solar magnetic field while orbiting the Sun at a distance comparable to that of Earth. Pioneer 9 was operational for a very long period of time, sending data until May 1983. 2 Helios spacecraft and the Skylab Apollo telescope mount gave researchers important new information about solar wind and the solar corona in the 1970s. The U.S. Germany-developed Helios 1 and 2 missions observed the solar wind from an orbit that placed them just inside Mercury's orbit at perihelion. The Apollo telescope mount was a solar observatory module that was part of the NASA-launched Skylab space station, which was manned by astronauts living there. The solar transition area and UV emissions from the solar corona were first observed in time-resolved fashion by Skylab. The first observations of coronal mass ejections, then known as coronal transients, and of coronal holes, now known to be closely linked to the solar wind, were among the discoveries. The abundances of iron group elements in the Sun were the subject of a lot of research in the 1970s. The hyperfine structures of several iron group elements, such as cobalt and manganese, made it difficult to detect their abundances using spectrography until 1978, despite much research in this area. In the 1960s, the first generally comprehensive set of oscillator strengths for singly ionized iron group elements were available. These oscillator strengths have since been enhanced. The abundances of the iron group's singly ionized elements were calculated in 1978. The existence of a gradient in the isotopic compositions of solar and planetary noble gases has been discussed by a number of authors. Examples include connections between the isotopic compositions of neon and xenon in the Sun and on the planets. Before 1983, it was believed that the solar atmosphere and the entire Sun shared the same chemical composition. It was asserted in 1983 that the isotopic composition link between the planetary and solar wind-implanted noble gases was generated by fractionation in the Sun itself.
Thank you for watching. View more our channel videos.